Kia ora and welcome to this video on question 2 of the Schol Calc Exam from 2023. This question is mainly set in the area of complex numbers. Part A is a trig problem. Part B, you can solve using trig, or you can just power the thing by 4. Part C is an interesting one. If you've never seen Euler's equation before, it's kind of there to give you a hint to solving the problems. It's a bit strange that you're asked to take the log of negative numbers and the log of imaginary numbers, because it's kind of an extension beyond what we cover in NCA complex numbers. When I first had that question, I was like, can you actually do that? And then I remembered my university maths. Part D is a locus problem to do with complex numbers. Right, let's get cracking. Okay, part A, just like our question 1 video, we're going to look at different ways to solving this problem. I've got 2 ways, although I'm sure there's many others. Part B, we're going to look at 2 methods, and then part C and D I've only found 1, so we'll just stick with that. Alrighty, part A, the easy way of solving this problem. Okay, you're told that cotan of x is equal to negative 5/12, and you're also told that x is in the fourth quadrant. Okay, that's important because the quadrants in trigonometry determine the sign of the values, and I'll talk a bit more about that later. But yeah, we're told here x is in the third quadrant. I keep saying that, fourth quadrant. We're actually wanting sine of x over 2, so we've got to decide what happens with x over 2. If x is between 3 pi over 2 and 2 pi, and we half that, we're inside the range of 3 pi over 4 and pi, which is actually second quadrant. So x over 2 is in Q2. That's important. Anyways, we continue with this. Cotan of x is minus 5 over 12 gives us a triangle. I'm going to ignore the signs and all the negatives and stuff at the moment, and I'm just going to draw a triangle with that relationship. Bear in mind that cotan is the reciprocal of tan, and tan is opposite over adjacent. So actually cotan is adjacent over opposite. The adjacent side would have to be 5, and the opposite side would have to be 12, and that gives a hypotenuse of 13 because it's a Pythagorean triple. Okay, so that's quite helpful. Now we need to think about the signs of things. For x, we're in the fourth quadrant. So in the fourth quadrant, we're in the last quarter of a trig curve. Okay, so sine, first quadrant and second quadrant are positive, third and fourth quadrant is negative, and cosine starts off positive, it's negative in the middle, and then ends positive. So in the fourth quadrant, cosine is positive. Okay, so from our triangle there, cosine of x is equal to 5 over 13, not negative 5 over 13. Okay, we do the adjacent side and we divide it by the hypotenuse to get cosine. And the reason I've got cosine is because we can use the double angle formula for cosine, which is this one, to relate 2x to x. Or in our case, we want to relate x to x over 2. So if I half this angle, I'm going to half the angle on the right-hand side. The double angle formula can also be written as cosine of x is equal to 1 minus 2 sine squared x over 2. And if I rearrange that equation, I've got sine of x over 2 is equal to 1 minus cosine x, all divided by 2, square rooted, plus or minus. And this is again where we need to consider the sign of the sine. X over 2 is now our argument, and it's in quadrant 2. So quadrant 2, what happens to the sine function? Well, quadrant 2, the sine function is positive, so we need to ignore the negative root there and go in Q2, sine of x over 2 will equal the positive root of this thing here, but remember that we already knew what cosine x was. Cosine x is 5/13, so we can replace the cosine x there with 5/13. 1 minus 5/13 all over 2, and if you simplify that, you get 4/13 or 2 over root 13. And that's the answer. The second way of solving this problem is to go directly from the cotan expression into the tan one. It's a little bit messier. Let's actually do this on the side here in a different colour pen. So I started off with knowing that cotan of x is equal to minus 5/12. I flipped this upside down because there's no trig identities. Well, actually there's one, but there's no double angle formulas for cotan on the formula sheet, but there is one for tan. So if I flip this upside down as minus 12/5, and then I use the formula tan of 2x is equal to 2 tan x all over 1 minus tan squared, but I play the same game as before. I replace the 2x and I half that angle and half the angles on the right hand side as well. Don't change the 2 that's in the front. It's a coefficient, not an angle. So I get a similar formula, tan x is equal to 2 tan x over 2, all divided by 1 minus tan squared x over 2. Now I can rearrange this equation because it's a quadratic equation. I know that tan of x is minus 12 over 5, so that's useful. Minus 12 over 5 multiplied by the denominator that's on the right hand side is equal to 2 tan of x over 2. If you don't like writing that out heaps of times, use a substitution like we did to solve the log equations in question 1. So wherever there's a tan, that's an awful colour to use, sorry about that. If I go tan of x over 2, replace that with u, then I'm going to have minus 12/5 1 minus u squared is equal to 2u. Rearranging this, you can check it comes out to a quadratic 12u squared minus 10u minus 12 equals 0, of which you can solve for u is equal to 3 over 2 or negative 2/3. And you kind of know you're on the right track when you get nice values like that. Remember that u is equal to tan of x over 2, and we need to determine whether tan is positive or negative. X over 2 is our argument. Remember that x over 2 falls in the second quadrant, and in the second quadrant, tan is negative. What you need to remember for quadrants, if we just have our quadrants here, all of the trig functions are positive in the first quadrant. Sine and cosine are, and therefore tan is, because tan is just sine over cosine, positive divided by positive. The sine one is positive in the second quadrant. Bear in mind we go anti-clockwise. Okay, the sine function is positive, but the others are negative. In quadrant 3, it's the tan one that's positive, because both sine and cosine are negative, and when we divide two negatives, we get a positive. And then lastly, cosine is the only one that's positive in quadrant 4. If you haven't seen this before, starting off with A, then going STC, I was told at school it's all science teachers cane. Caning got outruled. I was also taught when I became a teacher by a friendly colleague of mine that all strippers turn cold, and I remember that one more than the first one. So in this case, we're in quadrant 2, which means that our tan value, tan of x over 2, must be a negative number, and therefore tan of x over 2 is equal to negative 2/3. Often you'll rule out the negative, but be careful in trig ones you don't necessarily rule out the negative one. Okay, once we're there, we can draw another triangle. This time though, our angle is x over 2. And we know the tan ratio, so opposite is 2, adjacent is 3. I ignore the negative when I'm drawing a triangle like this. I just want to find the hypotenuse. 3 squared is 9, 2 squared is 4, add them together, you get root 13. And then the sine is opposite over hypotenuse. Opposite is 2, root 13 is the denominator there. And for the same reason as before, sine is positive, so we take the positive value there. Okay, question number 2 is a pretty straightforward complex numbers question. Really just achieve level skills here. Interesting that it's appeared in the scholarship exam, but it should give you confidence if you're good with your level 3 skills. We need to take a complex number here and power it by 4, but we have to take its conjugate first. Okay, I'm going to show you 2 ways. One is tedious, but the second method is definitely better. Okay, so z is equal to minus 1/2 plus root 3 over 2i. So z bar is equal to minus 1/2 minus root 3 over 2i, and we want to power this by 4. We can use the binomial expansion formula. If you've never seen this before, it's probably not the video to learn it, but search up binomial expansions. What I'm talking about here is a plus b to the 4. Our coefficients are 1, 4, 6, 4, 1. They come from the Pascal's triangle. So we've got one lot of negative 1/2 to the quarter, 4 lots of negative 1/2 cubed times by the next term minus root 3 over 2i just once, 6 lots of negative 1/2 squared times negative root 3 over 2i all squared, 4 lots of negative 1/2 just once with negative root 3 over 2i cubed, and then lastly 1 lot of negative root 3 over 2i to the power of 4. Now your graphics calculator is going to do a lot of this for you, but we are showing our working here. So negative 1/2 to the 4, the first term there is 1/16. The next term, you've got to be careful of this, it's 4, and then this dude here is minus 1/8, and then there's another minus 1/2 in there, and then there's a root 3i. So that all comes to be root 3 over 4 times I. I leave the root 3 in there rather than going to decimals. The third term there is a 6, then it's a quarter, another divided by 2, and an I squared, which is negative 1. And there's another minus in there as well, but it's been squared. So you've got to be real careful with integers here. It's very easy to make a mistake. I must say I did when I did the problem my first time around. Be minus 9/8. And then the last two terms come to be minus 3/4 root 3i and 9/16. Add the real terms together and add the imaginary terms separately. You end up getting minus 1/2 minus 1/2 root 3i, which turns out to be z bar. Interestingly, when you take the complex number z and you power it by 4, power its conjugate by 4, you get the same thing. Some of you are probably screaming at me, why did you use the binomial theorem? Because if it's a power of 4, you can square it and then square it again. Squaring's quite nice. It's just a binomial expansion, double brackets, and then square your result again once you've simplified it. So it's actually quicker to do it that way. But the question really, I think, was intending for you to use a de Moivre's theorem. So z bar, starting again, actually a different colour because it's a different method. Starting at z bar is minus 1/2 minus root 3 over 2i. As soon as you see a square root 3 or something in the problem, it looks like a special triangle. It actually is. So we can get some nice exact answers here. Make sure you put z bar in the correct quadrant. Minus 1/2 sits on the left of the origin, minus root 3 over 2 sits downwards. So we're here, that's z bar. I'll leave you to fill in these details, but you can find that this hypotenuse here is 1, and the angle is this way. If we go that way, it's a negative angle. Turns out to be minus 2 pi over 3. Okay, I found that using trig. This angle there is pi over 3, or 60 degrees, which means that the argument for this problem is negative 120 degrees. Degrees or radians is okay for this problem. So we turn z bar into polar form by writing it as 1 cis negative 2 pi over 3. Of course, you don't need to put the 1 there, but I just did for effect. The z bar to the 4 is therefore 1 to the power of 4 cis minus 2 pi over 3 times by 4. That's the theorem, DM theorem. Okay, and then one of the 4 is, of course, just 1, and cis minus 8 pi over 3. The question is, okay, well, where is minus 8 pi over 3? What you want to do is take away a multiple of 2 pi. 2 pi is a full circle. 2 pi is 6 pi over 3. So if we take away 6 pi over 3 from this, or add 6 pi over 3, we get to minus 2 pi over 3. They're the same angle. And of course, that takes us back to z bar. And the question asks us to answer in rectangular form, so we're going to write it as minus 1/2 minus root 3 over 2i. Alrighty, part C. Euler discovered an exponential equation, or exponential equivalent polar form for complex numbers. He found any complex number can be written in the form z equals r e to the I theta. I could have used that for the last question if I wanted to, but I chose cis notation because that's what NCS students will be more familiar with. From this, it can be shown that e to the I theta is equal to cos theta plus I sine theta. Use the identity or otherwise to determine a real value for I to the I squared. You can cheat on your graphics calculator. You can just type in I to the I all squared and it gives you a number. It's a decimal. Turns out it's actually a really nice decimal. It's related to the number e. We've got to prove that. And then the second one, log of the stuff we need to also find, but this time in rectangular form. Okay, so starting off, how does this connect to the e to the I theta formula? If you're watching this video, you're probably a maths nerd, which means you've probably seen some t-shirts that have e to the I pi equals cos pi plus I sine pi equals -1, because cosine pi is -1 and sine pi is nothing. If you've seen a shirt like that, you're in good company. It's a beautiful equation, e to the I pi equals -1. But we don't actually want this one. We want e to the I pi over 2. That's the first sneaky bit to notice, that this equation, if you sub theta equals pi over 2 into it, cosine pi over 2 is 0, and sine of pi over 2 is 1, so you get I out of it. And the question asked us to find I to the I and square it. Well, if that's I, then I to the power of I is going to be e to the I pi over 2 to the power of I. I don't rewrite it as e to the I pi over 2 again. I don't need to, because I can use power rules. Multiply the powers through. When it's written like that, you multiply the powers, you got I squared is -1, so you get e to the negative pi over 2, which you can confirm on your calculator is the decimal of I to the I. Question said I to the I squared, well, that's no problem. I to the I squared is equal to that thing squared, and we apply the power rule thing again by timesing the powers, and we get e to the minus pi. Okay, the second part II, which is kind of, looks almost like I to the I. It was this log thing, log of -25 e to the I to the I. Okay, we first up use log rules. So we split this, it's a product of things, because I can write it as log of -1 plus log of 25 plus log of e to the I to the I. And why have I done that? Well, the third term, log and e, natural log and e to the power are inverse functions of one another, so those will cancel each other. Log of 25 is a real number. The problem is, what is log of -1? I could cheat on the calculator and go, hey, what is log of -1? But I don't need to. I just use this relationship. E to the I pi is equal to -1 means the log of that will be I pi. So I get I pi plus log of 25, which you can write as log of 5 squared if you want, and then plus I to the I. And we've got one last decision to make. What do I do with the I to the I? Well, we've already seen that in the earlier working. So we've got log of 25 plus e to the minus pi over 2. That's the real part. And then we've got plus pi times I. That's the imaginary part. And that's in rectangular form. Pretty cool, huh? Okay, lastly, part D. The general equation of a circle is given by the following equation. Just think about what that means. You've got an x squared and a y squared term that have the same coefficient, and then you've got no minuses in there. So it's not like minus y squared, that would make a hyperbola. You've got a bx and a cy, so linear terms and a constant. So that's the equation of a circle if you were to expand things out. Normally we see equations of circles written in perfect square form, something like this. Okay, but if you were to expand that out, it would be a similar format. If z is a complex number, show that any circle can be written in the form alpha times z, z bar, plus beta times z, etc. You would never want to write a circle in that format, but we've got to show that they're equivalent. And I think it's easier for this question to substitute, like we normally do with NCA problems, substitute this into the expression and show that it comes out as the equation of a circle. Going backwards is a little bit trickier, and I'll leave that up to you to see if you can work it out. Okay, it also tells you that alpha and gamma need to be real constants, but beta may be non-real. Okay, so let's write out this equation that we're going to sub into. Part D. I should have enough space in this. We've got alpha z, z bar, plus beta times z, plus the conjugate of beta times the conjugate of z, plus gamma equals 0. Subbing in, so let z equal x plus iy, which we normally do, but I'm also going to let beta equal a complex number. Beta is going to equal p plus qi, 2 letters of the alphabet that won't get involved with all of the other letters in this problem. Okay, so if we substitute in, we've got alpha multiplied by x plus iy times x minus iy, plus p plus qi multiplied by x plus iy, plus p minus qi times x minus iy, and lastly gamma equals 0. If you're writing this in your exam, you're not allowed to go into the margins, so apologies for that. The first term there, when I multiply those brackets, it's a difference of 2 squares, so I get x squared plus y squared. We were expecting that. The next terms, if I expand out these brackets, I get p times x, and I get another px in that one, so 2px. I get a minus qy out of that, because I squared is -1, and I get another minus qi out of that one. Minus qy, so it's minus 2qy. Actually, all the other terms cancel. If you were to expand those brackets out, you'll see everything cancels. All the imaginary stuff cancels, which is needed. Because when we have an equation of a circle, we don't have any imaginary coefficients or imaginary terms. Otherwise, we wouldn't be able to graph it in the Cartesian plane. So, we've got that, and then we've got the extra gamma at the end. And all we need to do now is link it to the equation that was given to us. So if we let alpha equal to A, we let gamma equal D, we also need to let 2p is equal to B, the number in front of x, and minus 2q is equal to C. Well, these are all real numbers, so we can just swap out the letters like that, no problem. Then we get the equation A times x squared plus y squared plus bx plus cy plus d equals 0. They're equivalent. So we're proven. And one last little side note. It turns out that if that's the case, then beta is equal to b over 2 minus c over 2i. And that, if you're working the proof in the other direction, that's the connection that you need to make, which is a little bit trickier to find going backwards. Catch you in video 3.